Let's imagine we start out with some stationary fluid. I've drawn some ripples at the top here, not because we're assuming that there'll be ripples. If it's stationary, it'll be perfectly flat, but just to indicate that's the surface of the fluid. And then let's take a plate, and we're going to rest this plate horizontally on the surface of the fluid. And we'll assume that this this plate has some area A. Then we move the plate. We start moving the plate at some constant velocity. So we're going to move the plate at some constant velocity v. What's going to happen to the velocity of the fluid? Well, the fluid just below the plate we know we'll have to move at v, but then as we get lower and lower into the fluid, we should have a linear drop-off of the velocity from v to 0 at the bottom surface. The force that we have to apply to maintain this velocity, to keep that plate moving at a constant velocity, we find that the force is proportional to the velocity. The greater the velocity, the greater the amount of force we have to apply. It's proportional to the area. The larger the plate is, the greater the force. It's inversely proportional with the height z. The deeper it is, the slower the velocity has to change, and once we get it moving, the easier it will be to keep it moving. So inversely proportional to z. And then also with the viscosity. The more viscosity, the harder it is going to be to pull. Well, we'll make this into an equality, and we'll write that F is equal to V times A over Z, and then we'll introduce a constant that will represent the viscosity, and that is the Greek letter eta. This is a lowercase Greek letter eta. And eta is equal to the viscosity. So that's how we'll measure the viscosity. So what are the units of eta going to be? Let's see if I can fit it in over here. The units of eta will be, inverting this, it'll be the units of force, which will be newtons, the units of z, a distance, which will be meters, divided by units of velocity, which will be meters per second, divided by units of area, which will be meters squared. And so what we end up with are Newton seconds per meter squared. Newton second per meter squared. What is a Newton per meter? Well, that's a pressure, that's a Pascal. So this is a Pascal second. There we go. We'll leave it at that. That's the standard SI unit, a Pascal second for eta, the viscosity. Okay, very, very good. Going back to our pipe here, let's figure out what is that value R, the capital R, the resistance to flow. Let's imagine we've got some pipe with a length L and a radius R, starting out at some pressure at one end at P1 and the pressure at the other end at P2. What we have then is that the change in the pressure is equal to 8 eta, now we're not going to derive this, I'm just going to give you the result. 8 eta L over pi r to the fourth times the flow rate. In other words, that constant R, the constant of proportionality between the change in the pressure and the flow rate, is then this thing right here. 8 eta L over pi r to the fourth. There we go. This result is called PHYS2211 law. Okay. There's something very, very interesting here. And it's important, should be important to all of us for our health. Think about blood flow through our arteries. If you've got a nice large artery, you have a change in pressure across the length of your artery that looks something like this. Now, what happens if you have some buildup within your arteries, for example? Let's imagine that you've got some stuff building up in your arteries, decreasing the size of your arteries. let's imagine it changes so that now you have an opening that's maybe 1/2 the original radius. Well, what do you think? Just 1/2? That's not going to affect it too much. 1/2, we'll just change the pressure by, what, twice the pressure or something? Well, let's think about this. If we change this value to 1/2 its original value, what is 1/2 to the 4th? 1/2 to the 4th would be, well, 1/2 squared is 1/4, cubed is 1/8, 4th is 1/16. The pressure that would be involved to maintain the flow rate. Now, either the flow rate will decrease, which means you'll get 1/16 the amount of blood flowing through the artery, or your heart will have to work harder to increase the pressure by 16 times the pressure to maintain the flow rate. Well, what's going to happen is you're going to get something in between there. The pressure cannot increase by that much. The flow rate is going to have to decrease. Your heart's going to be working harder, and you still won't get as much blood flowing through your arteries. So, keep your arteries clean, eat well, exercise, etc., etc. Don't smoke. So, very, very interesting result, very important result. We can see the relationship here between the size of the opening, very, very strong dependence on the size of the opening and the pressure. Okay, very, very good. One thing that we still haven't taken a look at is compressibility. How can this compressibility and viscosity affect the flow? There's a very, very important quantity we have not considered. Let's take a look at one more thing. One thing we have been assuming is that as the fluid flows, it maintains whatever flow it has. If it's going in some nice straight lines like this, it's going to keep going in nice straight lines. But that's not always exactly what happens. We might start out with fluid flowing nice and smoothly, but then we end up with something happens and the fluid ends up mixing together. We end up with what is called turbulence, or turbulent flow. We don't end up with nice smooth flow like this, which is called laminar flow. We end up with things mixing together called turbulence, which completely changes the amount of flow rate that we can actually get through tubes. Now, what's going to determine whether we get turbulent flow or laminar flow? There is a quantity that helps describe the fluid called the Reynolds number. Let me actually erase this to give us a little more room. And it has to do with how much viscosity a fluid has. It depends on that for one thing. The Reynolds number, we'll call this N sub r, is equal to 2r, where r is the radius of the tube it's flowing through, rho, the density, v, the velocity of the fluid, divided by eta, the viscosity. Now if we look at the units of this thing, it turns out that it is unitless. I won't go through it. You can actually stick in all the units that we've looked at before, and you'll notice that they all cancel out, and it is a unitless quantity. So, how do we know? What are we going to get? Well, if the Reynolds number is less than around 2,000, we get nice, smooth flow. In other words, laminar flow. If we have a Reynolds number greater than about 3,000, we get turbulent flow. And if we have a Reynolds number in between, somewhere from, whoops, not lowercase n, greater than 2,000 and less than 3,000, we get unstable flow. It can switch back and forth from laminar to turbulent. And in that case, we get some very, very strange and changing flow patterns. All right, well, that's as far as we're going to go with that. what we're going to do next time is start taking a look at another kind of motion, and that is motion that repeats itself. In other words, oscillating motion or oscillations. That's what it is, oscillations and waves. All right, see you next time.